Good evening, everyone. Hope I'm audible to everyone. Okay.
Yes, sir. Good evening, sir. You're audible.
Thanks. So let's start. Uh, in this session, we are going to do revision for week 6, 7, week 5 and 6, and the time permits will go for week 7 as well. And for remaining weeks, we will do in some other session. Okay, so let's get started. Let me share my screen first. Well, is my screen visible?
Yes, sir, yes, it is
Yes,
visible.
sir.
So in week 5, as you know, we have done regression, and in week 6, we continue this for the regularized version of the linear regression part, right? So in yesterday's session as well, Karthik must have done some problems on regression and ridge regression or lasso regression. So that must have helped you to understand most of the part of week 5 and week 6. But anyway, we are going to do revise a quick revision of what we have seen in week 5 and week 6 here. Okay, so first, here. So in week 5, regression analysis, regression is there. So the setup is similar, the same, where we have the data matrix X of the shape D cross N. D is the number of features and another number of examples. So this every column of X now gonna represent a an example, right? So here X okay, here. So here every column in X denotes one example, and the associated label with that is y1 to yn, and that is in the label vector one, right? This is the general setup we have, right? And our goal is to minimize this. Not minimize. Our goal is to find the function that actually describe the relationship between these labels and the features, right? And so that function we are calling as h, and we generally call it as a model. So our goal is to find this function, this model, right? So that we can make use of that function to make the prediction for any unseen data point or even for the training data point, right? So here the HW, where W is the parameter, goes from RD to R. So we are defining the feature space, a function in the feature space that that actually is associated the label, any examples to its labels, right? So so underlying assumption here is that we assume that the labels are associated with features in some manner with some function f or some function s that we are trying to find out what function are generating those data set, those labels corresponding to those examples, right? And here we need to find those w, find those function, right? Okay, so for finding those functions, we have to design the metric that we can use to find out such function. Here we are defining a loss function, which we define as the what is the predicted value by using that function, and what is the actual labels, actual values for those data points that we have in the training examples. And for all such examples, we find the error and do the square, and then the sum over all those data points. That will be our total loss in the regression. And there may be different ways to define error as well, like absolute error you can define it, but this is the most general error we use in the regression, which is generally called sum of squared error as well. And even you can use the mean of squared error, when you can just simply put 1 by n here, and that will be your the result will be same for in both the cases, right? So generally we use this error for defining. So our task is to minimize this error. Once we have to find such those parameters or those functions which actually minimizes this error, right? And in our case, if we look at this function where we just map every data points to its own label, then if you look at this function, it actually minimizes error, because in this case the training error will be 0, right? But we don't accept this function, because our ultimate task is to find a model which we can use to make predictions for the unseen data point. But in this case, what's happening is just memorizing whatever is given in the training data set. That's not we want, right? We want something, a function, which actually capture the actual relationship between the labels and feature, not just memorize what is given in the training data set, right? So that's why we don't look for such functions, and we try to restrict our search space of the functions into the linear functions, right? And
Sir?
Yes.
So does that function memorize all the data points hwxi equal to
Yeah,
yi?
if you define the function, so that's how I define my function. I'm saying that I'm just mapping that function maps x size to its own label, right? In the training
Right.
example, so it's just like memorizing every data point. What's the label of that point?
Okay, so something will come out and that will memorize all the data point, huh?
Data point. That's it. That's what is this function doing.
Okay, fair enough.
It's not capturing the actual relationship between the labels and the features, right? So that's why we are not accepting this function. And what we are assuming that there's some linear relationship between the features. Let's say this we generally call as by hand. That's the prediction for the label for that particular example, right? So this is your data points, x data point where the features are x1 to xt, and we assume that the relationship between the features and the labels is linear relationship, and our statistic our search space to the linear functions only, right? And that's why we call it a linear regression problem. So here our task is to find these weight vectors W1 to Wt, and in the matrix vector notations form, you can write it as W transpose X, where W is D. W is just column vector of all the weight vectors W1 to Wt, and X is again your data points, right? So here is first features for that point up to real features for data points, right? And this is your data point. So this you can write as W transpose X. So this is the predictions for this particular data point. Yes.
Sir, I had a question here regarding this X point. Okay, so can you represent this X term, the data points in terms of X and Y coordinates, sir?
X and Y coordinate.
Yes, sir.
You mean
So
here
does it
in
take,
here
because
this
we are
data,
solving.
here this data points lies in a d-dimensional space. If I talk about this one feature, like let's say you have area of a land, and you are predicting the what if you have area and you're predicting the rent for that or whatever that you are trying to predict, right? So in this case, you have one-dimensional space and you have features here x, or say the area here and your predictions here, right? So in this case, you have points such n points, and you're trying to predict the function which actually those generating those data points. That's what we are doing here. So in this case, you have d-dimensional points. So you can think as every point into d-dimensional space. D plus one dimensional space. So y will be the output of that.
I have a question here. When we say 1 to D, we are talking about features of 1 point.
Here in this case, superscript is denoting the first feature. So this is first feature, the second feature, and this feature for that particular example X.
So we're weighting the features to get the Y.
To get the Y, right? We are using of those features, right? Those features can be area or whatever that you use, the number of BHKs, right? Like something like that. So this is your first feature, this is your second feature, or the locality can be another feature. So three features you have when you are predicting the price of that land or that house, whatever that is, right? So so these are your features, and you are making predictions using those features.
Okay, here is where I have a question. Just a little earlier, you were mentioning that this is a linear combination of things, and we are not actually seeing if they are the actual factors or not. Something like there's no relation is what you seem to suggest. I was not really clear about that part. The actual relationship, this is not the actual relationship. We are trying to find a relationship is what you just mentioned here.
So here I'm assuming that this data point, there is some function which is actually generating those data points. Let's say this function f, right? This function is f, and which are generating this data point with some noise, right? So this is noise you can call.
Okay.
Right. So our task is to find one approximate function for that we can use, make use of to approximate this function that we are looking for.
Oh, got it. Thank you.
Or in another sense, you can say that there is some relationship between the features and the buyer. That relationship we are trying to find. And here we are making assumption that the relationship between the labels and the features are a linear relationship. And we will break this assumption and we'll go to in more when we'll learn about the kernel regression or polynomial regression.
Okay, all right, got it. Thank you.
Okay. So now, since we have assumed we are restricting our space to the linear functions only, this is our predictions for any data point x, right? And now, what will be the error in this case? The error will be for this particular data point. This is the prediction, and true value will be by for that, and this will be the error for that. And similarly, we will do for all training examples and do the sum square and sum over all those data points. So this will be my error, and our task is to minimize this error, right? And so our optimization problem is what? We have to find the W for which this function is minimum. So this is optimization problem. Once we solve this, we have W and we have the function difference, right? So that's what we are doing here. Now, how to solve this optimization problem? This is very standard one that you solve, right? This is quadratic in W's. So this is a convex function, and how to solve this optimization problem? There are two ways that we have learned here. One is, okay, so this particular objective function, we can denote it as a vector notation as well. So here I'm doing sum over all those n examples. So what you can x transpose W minus y. So y is the label vector, and this is your data matrix. W is the weight vector, right? So if you look at this thing, if you expand this thing, you will notice that this is the same as this thing. Only this whatever I read. This is the vector notation for the same problem. So this is the norm of x transpose
Sir,
W
how
minus y.
did you say that this is a convex function?
So this is the you can think as a quadratic function, right? Quadratic function is true, or the polynomial function you can call this polynomial function of in variables W's, right? So every polynomial function is always not always convex function. So here in this is quadratic, something like this.
Yes.
So this is a
Polynomial of degree 2.
Degree 2,
quadratic function. Yeah.
But we just assume that actually this is a linear relationship. So how does this polynomial thing figure?
No. Here I'm calling it a quadratic function. So in general, if
This is actually the squared error. That's why we are getting a quadratic.
This is loss. This is your loss. Right?
Okay.
Not that function.
Okay.
Or even you can write it as x transpose, right? So this is A. So then you can write it as A transpose 0. So this is something. So your task is to minimize W's. So find W for which this function is meaning. Okay, so this you can solve it by using optimization problem. One is the general way that we do, like take the derivative with respect to the parameters and set to 0 and see at what values of W will give me the optimal values, right? So take the derivative. If you do these things, I'm not going to do here is that just take the derivative of these things and set to 0, then you will get that W is gonna be x transpose inverse xy. So this is your optimal solution of W, where the loss function is the minimum, right? But if you notice here, this is very computationally lengthy task, because here inverse is involved of x transpose. There are lots of examples, lots of features, then this is very computationally lengthy task. So this here we generally don't prefer to go in practice. So there's different ways to solve this optimization problem, which are called gradient methods. So what we do in gradient, okay, so before moving to gradient methods, there's one more thing that we have seen in the type, that is geometrical interpretation of these weight vectors. So how you can interpret these weight vectors. So just think like the same problem where you have two features F1, let's call this F1 and F2, or so in 3-dimensional space. So your X is looking like let's say you have the same example I'm taking, which is taken in the lecture. So like two features you have, and you have T cross N matrix. So 2 cross 3 matrix I'm taking here. So let's say you have examples of 50, 60. I'm not sure about what, but like 120, or say some other things like 50, 20, and just random values I'm picking up. So this is your first example. This is your second example. This is your third example. Let's say 28. Okay. So and the corresponding label is something 1, 2, 3. some random values are taken. Okay, so this is your features, right? So this is your first feature. This is your second features, right? So F1 is this one, F2 is this one, and so this is your first feature, and this is your second feature, and this is your bi-vector in three-dimensional space, right? So this is gonna be your span. You can think this plane as a span of these features F1 and F2. And if you look at the projections of bi
So
hat,
that is a y. That is a y actual, not the predicted one, right?
yes, sorry, this is by 2. By 2. Yeah. So this is the actual label, and this vector that is right. So if you this is the span, this plane you can think as a span of the features. I mean the or say the row space of X, right? Or so if you take this as a if you take the projections of by to this span, then it's gonna be somewhere here. So this is your projection here, and since this is projection, you call it by head, and this by head is since this is projection of this, you can write it X transpose some coefficient, right? Because linear combination of this F1 F2, because this is lying into the span of F1 and F2, so you can write it as a linear combination of the features F1 and F2. Right? If you set alpha value to W star that we got using solution of normal equation using normal equation like XX transpose inverse XY, then you say that this actually satisfies this equation. It means like this equation is so this perpendicular you can think as by hat minus by, and is perpendicular to each and every data points, right? So that equation, if you solve, that satisfies this one.
Sir, I get it, where the projection of a y on the y hat features, but I didn't get that this part. You said that okay, this is the W star is equals to X transpose pseudo inverse XY. So how it is linearly combining this feature?
No, I'm taking projection of this into projection of y into the span of this thing, right? So it means that I'm saying this y hat is lying in the span of F1 and F2.
Yeah,
What
okay.
does span mean? So it span means that y hat can be written as a linear combination of the features F1 and F2. That's what I'm saying here.
Okay.
Okay, so y hat is on that plane, the span of F1 and F2, right?
Yeah.
And y is on some other plane.
Y is?
Actual y is on some other plane. That is not
So
on
all these features for F1, F2, and y all lying in the three-dimensional space. Okay, give me 1 minute. I'll be back in 2 minutes. Just give me 2 minutes. So sorry about that. So someone was asking a question, right? What is that?
Sorry, sir.
Yeah, I was asking, sir, that F1 and F2, the y hat is on the, the same space of the linear combination of F1 and F2, and actual y is actually in the different plane, right?
Different space, right? So all these F1, F2, and y are lying in a three-dimensional space. So if you call this is your F1, so this is your F1, right? So this 50, 60, 120, this is your F1. Similarly, this is your F2, and this is your y. So all these are lying into three-dimensional space.
Okay. Let me redefine.
So
my doubt, sir.
this space you can call as the row space of X.
Yeah, let me redefine my question. From the figure, it seems that F1 and F2 are lying on XY plane, and Y actually is lying on Z plane. That is as per the picture that comes out. That F1 and F2 is lying on XY plane. If I take the x-axis as and then y-axis and then z-axis, so F1 and F2 are lying on the XY plane, and actual Y is lying on Z plane.
What is Z plane?
Sorry, Z-axis. So YZ plane. Sorry, YZ.
Y is somewhere in the space.
Okay.
Okay, this is some point in the space where I'm taking projection. Here is this pi hat, and I'm calling this as X transpose some alpha, right? Because I'm taking this as in the span of F1, F2. So this I can write as a linear combination of that point.
So F1 and F2 are on XY plane.
Just
For
think
example,
those two vectors. If you think as a x in the x plane, x-axis, y-axis, so your first picture gonna be like 1, 0, 0, something like that, or second picture is 0, 1, 1, 1. So there is two vectors in some space, three-dimensional space, and this plane is gonna be the span of those vectors F1 and F2.
So for F1 and F2, Z will be always 0. No? If you if you if, if you present F1 vector in the coordinate system 1, 0, 0, so it means I mean to say that Z is always 0 for F1 and for F2 also.
No, it's not like I'm taking this always on x-axis or y-axis. There are some vectors F1 and F2. Just to visualize all this thing, I just taken on the some plane that you're thinking as x plane or by x-axis or y-axis. It can be any two vectors in the space.
Okay, got it.
So I have a quick
Is
question.
alpha
With
equivalent
X
to
transpose alpha, so at the moment, when you say y hat is equal to X transpose alpha star, this alpha is not defined as yet, right? We are saying there is some combination. So what exactly is this alpha star?
So here I'm just calling it as calling this by as a linear combination of the data points. So let's call F1 alpha 1 F1 plus alpha 2 F2, right? So that's what I can write for some alphas, right?
Okay, so basically some kind of weights or some linear combination,
Yes, some linear combination of F1 and F2 that I can
Okay.
ensure, right?
Okay, and then in the next step we are defining alpha as
and I'm saying that this W star actually satisfies this property, like because this is space, like then it must be like this should be perpendicular to this thing, right? So this is what this vector is gonna be your, this is by vector, this is your by hat vector. So what is this? This is your by minus by hat, right?
yes, sir.
So this is perpendicular to this, so I can call it by minus by hat transpose. By hat is always 0, right? So this property must be satisfied. So if I put by hat equal to X transpose alpha here, then this becomes by minus X transpose alpha and transpose X transpose alpha. So this must be 0, right? This must be 0 always. So I'm saying this if I set alpha to be W star, this is satisfied. This equation is satisfied. So alpha equal to W star is one of the solution of that. Right? So this y hat you can write as X transpose W. Right?
Okay.
And what was that? That was the prediction, right? Remember, this was a
Correct.
prediction
Yes,
for
sir.
that training examples, right? So you can
Yes.
think the predictions as the projection of y, true y or label vector onto the span of the features. So that is a takeaway from this slide. So you can call it the prediction, right?
So
Yes,
basically,
got
we're
it.
trying to establish a relationship between alpha and W.
Or you can think this result, the prediction of training examples or data set.
Based on training example, yeah.
Data prediction of data is projection of label vector, right?
So one more confusion, sir. So y hat and the difference between y and y hat and the actual y, the multiplication, they are orthogonal. So can you please elaborate that which line is y minus y hat and which is y here?
This is your y hat. This vector is y hat.
Okay.
Right? And this is this vector. This is your y vector. So
Okay.
what is gonna be this vector?
Y minus y hat, yeah.
Right.
Okay, then okay, y hat, okay, y hat, and okay, they are orthogonal. Okay.
So got
So
it. Thank
you
you.
can think prediction as the projection of the level vector onto the span of f1 and f2, the span of features per se. So this is the all that we are trying to figure out.
Yeah.
Okay, so one way we have seen like finding the solution of this optimal problem as setting the derivative to 0 and find the W vector, right? And other different ways of doing the same optimization problem is solving the optimization problem is the gradient methods. And what we do here in this case, so what is gradient? Gradient of a scalar function f. How do you define? Let's say this is a function of three values, variable x, y, and z. How do you define a gradient of a function?
Do you
So
have
gradient.
It's a
to
partial derivative with respect to x, y,
X,
z.
Y, Z?
Yeah. So gradient actually is at a point is actually give the directions of the maximum change at that function. So this is a vector at that point. So this is del f by del x, del f by del y, del f by del z, right? And this actually gives you the This actually gives the direction of the maximum change, right? Directions of maximum change. So that idea we are gonna use in the gradient descent. What we do, we have some loss function. Let's say this is your loss function L of W, and this is your parameter W, right? And now we start at some random point. Let's say this random point here W, right? So at W we have started. This is some random point. Now what we want to do, we have to want to go in this direction where this function is minimum, where loss is minimum. So how we will move? You started at some point in the loss function and you want to go into this direction. So as you know, at this point that gradient will be what? Gradient will be direction of the maximum change, right? So gradient will be somewhere here and you want to move into this direction. So you have some initialization for W and you want to move into the minimum of the gradient. So you want to move in the direction of the del f, right? Negative of del f. So you just take del f, move into the direction of that loss function. So here I'm calling it LW. And how much to move into direction is decided by a constant which is called step, or say it decides. It's called the learning rate, and it decides how much to move into that direction, right? So let's say at the first station, this is your initial weight vector somewhere here, and in the loss function you are at this point now you want to move this direction. So you find the gradient at that point, and you see you have to move into this direction, and you have moved into this up to here, right? So this is your next W1, updated W1. So this is gonna be your W1. Similarly, you find the gradient at W1 and move into negative or gradient direction. So let's say you have at some point here. So this is your next W2. Similarly, you find the gradient at this point, and you keep on moving till the convergence. Convergence means your loss is minimum, right? And if you notice that losses keep on increasing, then you are moving into so what happens is the gradient descent, if somehow you move into the opposite direction. Let's say you have set eta to be large and you have moved to this direction. So what will happen in this case? In this case, the gradient will say that now move into this direction because you have find the gradient at that point, and that gradient will tell you that now move into this direction, right? So there may be case like if you set eta to be very high, then you started at some point and you just jump to this point, just jump the minima, and again you find the gradient, and gradient says that move into this direction. Then you have come to this point, and you keep on oscillating around the minimum. In this case, what will be the ideal solution for that? What is the wrong? You are taking very high steps, right, in this direction. So the ideal solution in this case should be you should decrease the learning rate, because you are noticing that the loss function is not minimizing, it just keep on increasing, decreasing, something that is oscillating around the minimum point. So in this case, you should decrease the learning rate, right? So this is what learning gradient descent says. Right? So this is the updates rule.
Sir,
Yes.
Can I ask?
actually, I understood the gradient part, but I'm very confused about the direction part, like in which direction it's moving to be like the change is maximum. So how do you know the change is maximum in that direction?
So great. I'm not going to the proof that gradient gives the change, the direction of the direction of the maximum change. Just remember this thing now, that the gradient of a function at that point gives the direction of the maximum change. Let's say this is your loss function. So this is your loss function, or say this is your function f, right? So here we are only considering the loss function. So this is loss function. If we are at this point, if you find the gradient at this point, the gradient is the direction where the change is maximum. Change means if this is your W0, right? So if you change that in the W, the function value changes maximum in this direction.
Why
Right?
not in the opposite direction?
This direction loss is minimizing, right?
Okay.
Here some value of loss, here some value of loss. So here it's loss is minimizing. So if you so gradient is actually giving this direction, and where you want to move into the negative direction of the gradient. So you want to move there, right? That's why we start some point and move into the opposite direction of the gradient. Right, and how much move is decided by this. So this is the update rule for gradient descent. At the tier iteration, you have weight vector WT, and now you at that point you find the gradient of the loss function. So this is your loss function, and you move into opposite direction of that gradient, right? By the step size eta. So this is your learning rate.
May I ask a question?
Yes, sir.
Yeah. So this is the second approach. Instead of going for minimization of loss, we are trying to find the gradient of this and see what is the minimum for minimum value for this function, right?
Yes, yeah.
Minimum value for W vector, yeah, that
Minimum value
minimum
for W vector. Okay.
Yes.
Minimum value for W, not minimum value for what value of W the function is minimum.
Yes, that's what.
Sorry, what value the function is?
For what value of W the function is minimum.
The function is, sorry, the last part, can you repeat that function is?
So we are looking at the W for which the loss function is minimum. We are looking at this
minimum,
W, right?
okay, minimum. That word was, okay. It is not clear to me, sorry. Thank you.
Sir, going back to that figure, so just it will take only 10 seconds.
Mhm.
Yeah, that figure itself, sir, that loss function figure. No, just now we drew that figure of loss function. Yeah, this one, sir, this one. So say for example, this at W0, this is one particular vector, right?
Mhm.
And this total loss, this is a summation of loss of all the data points, right?
This is loss function that you define as S transpose W minus pi.
Correct. So no, just intuitively I'm trying to understand. This is the cumulative loss of all the data points, right?
Yes.
Okay. Fine.
This is a function of W, right? That you agree, right?
Yeah,
This is a function of W.
got it, sir. Yeah, that's why I said I will take only 10 seconds. Yes.
So could you
And
just stop at this slide just once? Yeah. No, the next one. Thank you. Just one sec.
so what is the significance of eta here again? Can you please tell?
Eta, likewise, let's say you have this loss function, okay, and you have started here and you want to reach here, right? So how much to move into this direction? If you set eta to be higher value, it may be the case that you have jumped this value and reached the right. And if you have set eta to be very low value and you are moving to the right direction but very slowly, right? So how much to move is decided by this eta.
So what is the range of eta? Like how much is the
Generally it is said to be low value, like 0.1 value, or on the log scale you can decide of these eta values. So 0.1, 0.01, or let's say 1, 10, something. On the log scale you can decide eta values and check how your loss is changing on that. And so it's a hyperparameter. In generally you can tune these parameters. So now you can think as it's a constant value, but just remember thing is decides how much to move into that direction. That's
okay.
So now it's sufficient to move. Okay, so what happened in the stochastic gradient descent? Rather than taking here, we are considering for finding the gradient at every point. We consider each and every data points, right? So rather than considering each and every data point, what we do in stochastic gradient descent, we take the bunch of data points. Like let's say you have 1,000 data points, so you take some batch of 10 batches of size 100. Let's say 10 batches of size 100. So what you do, you find you have at some point here W. So you are calculating gradient. So for calculating gradient, you just don't make use of all 1,000 points. You make use of some 100 data points, and that direction is not gonna be a true gradient direction, but once you keep on doing the same thing, I mean the updating weight vectors on an average, you will move into the right directions. Okay, so we are not going to see the formal proof of that, how the stochastic gradient descent always move into the, I mean, gonna be give the right directions, but just assume that on an average, this is actually moving into the right directions. So that's the only difference in the gradient descent and stochastic gradient descent. For calculating the gradients, we make use of these batches of data points rather than considering all the data points, right? And in the last, we take the final weight vectors as the final the one optimal weight vectors. Okay.
Sir, one question.
Hmm.
What is the analytical approach?
Analytical is one that we said we take the derivative of loss function with respect to the parameters, and then set it to 0 and find the that critical constant.
Right, sir. Got it.
Sorry, once again, can you please repeat that? Analytical is you're referring to again the stochastic, the gradient descent formula or something else?
That normal equation that we mentioned before, right? The loss function take the derivative of with respect to parameter and set to 0. And then W comes as XS transpose inverse X.
Right. Thanks.
So any other doubts till this point?
No, sir.
So mostly we are done, right? So where we started with, we saying that we are trying to find a function which actually captures the relationship between the labels and the features, and we assume that the relationship is actually linear one, and we are trying to find that relationship. So this is your W transpose X, right? So we are finding these W's, and W, we end up with one optimization problem that we have solved using normal equation and the gradient descent method. And the normal equations give the W star as XX transpose inverse X, right? So this is what we started with, and we are done with that. Now we are seeing the same problem with a different root. We are seeing in the probabilistic view of this linearization problem. So our assumption is the same again. We are saying that these data points are actually coming from some function f, and for now I'm assuming that this the relationship between the features and label are still linear. I'm saying that this function is linear one, and but the data points are coming with some noise, right? So this is some error, right? So this is error here, and I'm assuming that this function, right? So this by head is actually W transpose X with some noise, right? So every data point, so this is the function which is generating this data point. So our task is to find this function. So here the assumption is that the noise is actually Gaussian with mean 0 and some variance sigma square. So this is the assumption of the linear regression model. And even we can break this assumption and we can go to the generalized linear models, but that is not covered for now, right? So just assume that this noise that we are talking about follows Gaussian with mean 0 and with some variance. Okay, so this is the assumption, and now our task is to find this W. So you can think, since epsilon follows normal with mean 0, so what will be the distribution of this thing? This is same thing, like we know that X follows normal with some mean mu sigma square, right? So what is the distribution of AX plus B? It follows normal with mean A mu plus B, and this gonna be variance A square sigma square, right? So the same thing. So here's epsilon follows normal 0 sigma square. So this thing gonna be normal with mean W transpose X size and variance sigma square, right? So this is now distribution of xi and yi. So your data points are coming from these distributions, and now our task is to find this parameter, because W is the unknown parameter. So we have landed up with the estimation problem. You have to estimate this parameters of this distribution, and we know how to estimate those things, right? We have very well-known algorithm for that, which is called the maximum likelihood estimate. So what we do in that maximum likelihood estimate, we collect some observations from these distributions, and in our case, we have training data set, right, with us. So that observations are those training data points, and then we can find the likelihood for these observations and take the and then maximize those likelihood for the parameters, right? So this very known maximum likelihood estimation problem. So solve this estimation problem, we landed up
Can you
with
just slow down a little bit, please? Can you just slow down? We assume that there is a kind of a distribution over there.
Mhm.
And that is a distribution that is going to be there, not just for the noise itself, but also for the W. So we are getting normal distribution for the mean and the variance. Is that correct so far? Y given X.
normal distribution for the mean and
So the line itself is represented by WTX, correct? W transpose X.
yeah, this line. Yeah, this line.
And the noise is represented by epsilon, which is having a variance of sigma square.
Sigma square, yes.
And from there, we are assuming, but then now the data points are not there already, right? What you just said a little later after the slide.
So till this point, everything is clear, right? So that
That
noise
point is
follows
clear.
normal,
Yes.
right?
Yes. Yes.
Now that's
So-
what we are making assumption that like by i's given xi are coming from some function which is W transpose xi, but with some noise added to this, right?
Yes.
And this noise is following Gaussian with mean 0 and sigma square.
This is
So,
clear.
so noise is always this, or we are assuming it can be any distribution. Noise can be from any distribution.
If you do some different I mean if you do the Laplace, then it may end up with some different optimization problem. Like
Okay.
Laplace actually refers to the one which is if you take the linear regression model with the absolute error, right? And some other function, if you exponential family and all, then you will end up with some different generalized models of that. But this is the most familiar assumption or most general assumption about the noise. That
Sir,
it follows Gaussian
sir,
with
this is the same thing. So you are saying the noise will follow the normal distribution with a zero mean and the sigma square as a variance, right?
variance of that.
In the
Yes.
second line, you have mentioned here is the x is following the normal distribution. So you mean to say the
No,
both-
I'm not saying x is following distribution. I'm saying by I given xi is following normal distribution.
So can you come again, sir? Can you repeat the last?
So till this point is clear. Like this by I
Yes,
xi I can write as W transpose
Yes, sir.
xi plus epsilon, right?
Correct.
Now this epsilon is following normal with mean 0 sigma square. So what will be the distribution of this? This you can think as a b plus a epsilon, right? B plus a epsilon. So what will be the distribution of this thing? This is again normal, right?
Okay, so you mean to say normal plus any distribution will be normal distribution.
Yeah, linear combination of the normal distributions are normal if they are independent. So here is just translation and the contraction of that. So this is ax plus b is again normal. This is very fundamental result of statistics, right? So if x is normal mu sigma square, then ax plus b is again in normal with a
So
mu
if,
plus
if
b.
we add any constant in normal, it will be a normal. No? I think.
Yes, again is normal, right? That's what I'm using here. So by I given x follows normal distribution with the mean W transpose xi and sigma square. So here W is the unknown parameter. That what we know is that the by I given xi's are coming from this distribution, but with some unknown parameter W. And now our task is to estimate this W.
Why are we calling it y given x? Okay, I understand that actually it is dependent on x, but when we say y given x, are we actually making an assumption there?
So this is given a data point. What is the level for that? That's it. You can read it as I mean for a data point. What is the level for that? Right?
xi is a data point, any data point.
Yeah.
Okay. And that data point distribution, the noise of the data points is assumed to be normal.
Normal is.
No, all those data points.
So is there any method to identify like what distribution my error is following? As you said that it may follow Laplace, it may follow other distribution also. So in real life, is there
No,
any-
I'm not saying that it may follow what error is following. That we never know. But in general, we start with
Okay,
assumption
we
and go
assume,
for
yes,
this
we
function.
assume, yes. Okay.
Okay, so this estimation problem, I think you must have done lots of time, right? This finding the estimation of parameters. So the same thing, the observations are coming from the normal distribution with some unknown parameters and find the estimation for those parameters. The same thing we are going to do that. We will collect some observation. In this case, it's training example. We will find the likelihood for that observation and try to maximize that, right? So that particular thing that you can do, and you will end up with this particular optimization problem. Like when you try to maximize your likelihood, you will end up with this thing. So here it's gonna be this maximizing this thing, minus of yi minus w times to the xi to square and to this thing. So or this particular thing you can even write as minimizing over this thing. I just remove the minus sign, right? And this is constant, so it won't affect. So this particular problem we have already seen, right, in the linear regression model, and we have solved it already. So what it says that the maximum likelihood.
Why is it argmax and why are we calling it as minus of?
If you solve this
Okay, e power. Sorry, that
Yeah,
is
yeah. After
okay,
taking
okay. Sorry.
So what
Really
this
sorry.
tells that the maximum likelihood estimate for W, assuming the zero mean Gaussian noise, the same as the linear regression model with the square loss. Remember when we started with the square loss, we ended up with this optimization problem. And
Sorry,
we are again with the same optimization problem.
Yeah.
So the maximum likelihood estimate for W with zero mean Gaussian noise is the same as linear regression model with the square loss.
Got it, sir. Okay.
So any other doubt?
No, sir. From this, no.
Sir, could you please scroll up a second?
Why is it summation?
Which one? You will find a likelihood. What is likelihood? Just take the PDF for every data point and the product of those things, right? And then you take the log likelihood for
Okay,
that.
and that e to power that would be.
Yes. For every data point, you do the same thing.
Okay, thank you.
Sir, does it have any relation between the W star you have found earlier, that X transpose, that inverse and XY? So are those same, sir? I mean, it's just a way of writing a different way. This is in terms of writing a loss, and that one.
So there again, right?
Yeah.
So there we have started with the square loss, and we were saying that this was our optimization problem. Here again, we are thinking it as an estimation problem, and again saying that this is the optimization problem. So you can think this estimate achieving zero mean Gaussian noise is the same as the linear regression model with the squared loss. Okay, and even you can prove that the maximum likelihood estimate for W, assuming the zero mean Laplace noise, is same as the linear regression model with the absolute error.
So Laplace I'll come later. So, sir, in terms of machine learning, okay, the in reference to the last chapter, week 5. So W, like whatever this one, okay. So W is a weight vector. In this direction, that loss is minimum. Can I take it in that word, sir?
At that point, the loss is minimum. If you solve it as a normal equation, then you will end up with
vector, right? Yeah. So W star is a weightage vector in this direction. I mean, when you use this, loss will be minimum. Correct?
Yes.
So we can relate these two terms. All right, sir. That's right.
Sir, just what Hari was saying, sir, just taking that forward. I know, both these two are same, and sir has done the derivation also, right?
Yeah.
We have landed at the same point, and that's why you have also written W star equal to XX transpose inverse XY. I have just out of curiosity, I'm asking, when through the ordinary linear regression model, we had established that, I am getting an error. So what was the need to go for Y given Xi, this kind of probabilistic approach?
No, this is the same thing, but the different views of that, different point of view. Here we are thinking as a
That's what I'm
probabilistic view
asking.
of the.
Yeah, what is the trigger point for that? This is just one approach, huh? That much only we can say.
Yes, probabilistic view of the same problem.
Okay, fair enough. Yeah, because this derivation sir has also done, and we
What derivation?
This that what you have proven, no, that we are getting the same error function, so we are getting the same W star. Yeah, fair enough, sir. You are saying that this is one more approach. Yeah. Okay.
Just a simple question, as in just for completeness, so that because I'm getting confused. Sometimes prof writes arg min, sometimes he writes min, right? But in linear regression, all the time it's like technically it's arg min only, right? Because we're looking
arg min means the parameter value you are looking for.
Correct, where the function gets maximized or minimized.
Yes.
Otherwise, argument also you're looking for that parameter, but you're more like your final output will be the overall value, not the argument value. That's the only difference, right?
If you're looking at like minimum, then you're looking at the minimum value of the function. That is the technique.
Correct. So if you look at some correct. So if you look at some of our prof notes, Like he initially said it's min W, the X transpose W minus Y, but that should be arg min, right? Technically, you're looking for.
Maybe professor must have written like something like this, right? So you can think like this is that solving for W for which this is minimum. Or it's the same thing. Don't be confused.
I'm saying technically it should have written arg min, right? That would have been better.
Right. Yes, would be better. Right.
Yeah.
So technically, what is the difference between both two? So like sometimes we write mean and sometimes we write arg mean.
So minimum is that minimum value of the function, and arg min is that the value of the parameter at which the function is minimum.
Value of the parameter at which
the function is minimum.
Okay.
Let's say x square. X square is function. What is the minimum value for that? 0, right?
0,
at which this is 0, 0. In this case, 0, but if let's say x minus 1 square. So what is the minimum value? 0. At which it is minimum? 1 it is minimum. So this is arg min, and this is your x value, and this is the function value, minimum function value.
Okay.
Both the times we are minimizing the function only. In one case, we want the output.
One case we are
argument.
We are reporting the minimum function value, and here we are reporting the
correct. The output we are looking for is slightly different.
Yeah. So minimum parameter, value of the parameter is the function is minimum.
Correct,
Yes,
correct.
got it. Thank you.
You were asking that question, GP. Can you go ahead, or you got the answer?
I was done. I got it. Thank you, Vasu.
No, I didn't hear it, so I was on.
Yeah, thank you.
Okay. Okay, so if there is no question, we can move ahead, right? To next part of that.
Yes, sir.
Okay. So, okay, so till now we are making assumption that the labels have linear relationship with the features. Right now we are gonna break this assumption, and now we are saying that the relationship can be any complex relationship, right? And so, like, let's say this is your relationship. Let's say some sine function, or say something. This is your actual function where the data points are coming from that, right? And some with some noise. We are going to learn this function. So how to do this? What we will do, rather than doing learning the linear function, what we'll do, we'll learn the polynomial functions of some degree. Let's say of degree p. So what we will do, we'll try to learn the function of xp is to x. If your features are x1, x2, x3, so you are learning like x1 raised to power p plus x2 raised to power p, or some x1 raised to power p minus 1, x2, something like that, right? So x1, x2. These are your features, and some p degree polynomial you are learning. So this is your weight vector w0, w1 up to w4. Now what you will learn, you will learn polynomial functions of that rather than linear function of that. There is trick for doing these things. Rather than learning all these things, we will apply the kernel trick. And the kernel trick applies when we are sure that the weight vectors can be written as a linear function of the data points, right? That we approve, right? That weight vectors can be written as a linear combination of data points. So here in the kernel trick, what we will do, we'll transform our data points. Let's say your x is the data points where we have some non-linear relationship between the features and labels. Now what we will do, we transform this data point into some higher dimensional space using some mapping phi, and this is your transform data points. Now what we are saying that in this transform space, your data points, so this data point phi x1 up to phi xn has linear relationships, right? So once we have this mapping, now we can apply the linear regression model into the higher dimensional space, this transform space. Okay, and for that we will use the kernel tricks, because and how we can use the kernel tricks? Once we have made sure that our W vectors can be written as a linear combination of the data points, then we can apply the kernel tricks. And that proof I'm not gonna do here, but you can check the slides. It's pretty easy how you can see that And here I'm saying that W star can be written as a linear combination of data points. It means your transform data points are phi x, right? So W star I can write as phi of x times some linear combination of those data points, right? And this is your solution for normal that we got from the normal equations. Now in the transform space, your data points are linearly related to y. So then you can apply the linear regression model to that data point, and this will gonna be a solution for that. And I'm assuming that this is so this result I'm applying here. I'm just substitute W star to be phi of x into alpha. Our task is to find this alpha. Okay, so just solve this equation for just do the manipulations of here and there. You will find that this alpha it can be written as k inverse y, where k is your that kernel matrix that you call phi x and phi x transpose, right?
Could you please go back to that where alpha comes in?
Right. So this statement we are saying that the weight vectors can be written as, I think I must have written here. Not here, but so this result you can prove that the weight vectors can be written as the linear combination of the data points. So this proof you can check it out. It's fair easy to prove. So once you have this thing, it means that the W star is
We did something similar in PC, I suppose, yeah? Where we express the weight vector as linear combination of the data points.
So alpha equal to beta upon underscore n lambda, right? That's how. So that's the same way we are trying to find the alpha.
Something similar, yeah.
Yeah.
So here also we are doing the same thing. The weight vectors we are treating as a linear combination of data points. Once we prove this, I can write in the higher space my data points are phi x1 to phi xn. I mean the data matrix is phi of x, right? And so the W vector I can write as a linear combination of that thing. And if I apply the linear regression model into the transform data point, this is my weight vector, right? So this is like x transpose inverse xy, right? So same thing, but the data matrix is phi of x. Okay, and I'm substituting W star to be this thing that we are achieving. Okay, now our task is to find alpha. Once I have alpha, I have the weight vectors, right? I'm not gonna go using this method, because in this method I am to find this phi and then transform every data point, then find all these things. So it's very computational lengthy part. So this short trick I'm applying, or you can say it like. So this alpha I need to find. So alpha I can find at k inverse this. If you solve these terms, you will say k inverse phi, and k is what? K is your kernel matrix phi x transpose, right? We are, or the kernel. If you remember in the week 2 we have seen that this the matrix element ith element is of this kernel xi, right? So this is going to be your n cross n matrix. Okay, so for every for any transformation, you have a valid kernel, right? So for that kernel function, we will make use of for finding this k. Once we have k, we have alpha, and once we have alpha, we have W vectors, right? So W vector is going to be phi of x times alpha. So again, you need phi to find the W weight vectors, W vector here, but we are not actually looking for the actual values for W. What we can do is we can just use those things to find the making predictions, right? So for making prediction, what is the prediction for the data point xt? You will transform again this data point into higher dimension. That is gonna be phi of xt. In this space, again, what is your prediction? This is your this is your model, right? W transpose xi. Right, so this was your model. So I will just put this value here. So this thing, and what was your W? W was this thing, right? Linear combination of the data points, right? So W was this thing, right? And if you solve this, you will get this this can be written as alpha I k xi xt. So the idea is that you can avoid use of alpha, right? You don't need alpha at all. Just you need to the valid kernel corresponding to that phi. Once you have this thing, this is the prediction for that particular data points. Alpha I k xi xt.
Excuse me, but could you go to the previous slides? It went by a little fast for me. Sorry, can you scroll up a little bit, please? The previous slide. Yeah, here we are actually having, okay, we're calling W, we're calling it as phi alpha x, okay.
Okay, so it's one correction. one correction. This K matrix should be sorry, where I mentioned as XX transpose, right? So it should be X transpose X, not XX transpose. XX transpose is the K covariance matrix. So this K is phi X transpose phi X, right? Not this thing. I mean this thing, right?
So for finding alpha, we need to find the K inverse itself now.
K inverse.
After finding the K, we'll find the K.
K
Okay,
inverse.
is given in the question. Kernel matrix.
Sir, then how to find this kernel matrix, sir? I mean, can you take some small example to understand this thing, sir? If possible, if time permits, we can take.
Yeah, of course, of course, of course.
Otherwise, this confusion will still going on, sir. I mean,
Uh, just one interruption, please.
Is the
W is
can you
assumed
please-
as phi x alpha, is it?
Sir,
Sorry?
can you just go back to the slide, sir? The one
I just
above.
missed
The
what
one
you
above.
said.
Yeah, this no, the one above. The one above. This one, yeah. So here inside it should be X transpose, right? First should be 5X transpose.
Sorry.
The first term should be phi of X transpose into 5 of X, right?
No. W vector was what? W vector was like this thing, right? XX transpose
X X transpose. Correct.
XY. So
Correct.
this is just matrix is phi X here in this case.
Got it.
So here we're assuming W to be phi x alpha.
Phi X alpha, linear combination of the data points.
Okay. Then the next slide, can you please pause there a little bit? Okay, phi x we're removing and we're calling it as alpha is equal to K inverse of Y.
Yeah.
Uh,
Okay.
Ravi, can I interrupt? This is
Sure,
coming. So what happened? Like in the slides lectures, sir added x on both the sides. So then there's a combination of XX transpose, and then on the left hand side it was XX transpose squared. On the right hand side it was XX transpose. So that's how this comes as 1 by K
Oh,
Y. That's
okay.
why it is K. So you the reason I'm telling you is this: if you go to the slides, you will be able to figure out the link between the equation above and this one.
Okay. All right. Thank you, Cheryl.
Yeah.
Okay, so for example, just do one example quickly here to summarize all these things. Okay, for
Could
this
you
kernel
pause
part.
on the next slide, please? Could you just pause on the next slide? Yeah, just pause for a second.
so now you go for example, sir.
Sir, just one question. X is D cross N or N cross D?
Which X? This X?
The original X data matrix.
This is again D cross N. The
D
same
cross
thing.
N, right, sir?
This phi of X will become some D cross N.
Right, sir.
It's-
So if I have a one-dimensional data set, then the covariance matrix essentially transforms into a single digit, right?
Sorry.
If I
Covariance
have a
matrix.
data set of one dimension, like I have a
Yeah,
data
then
set of
it is
1,
1
2, 3,
cross. Yeah.
then the covariance matrix becomes a single scalar value.
Yeah,
Yes.
it is basically the variance of
Right.
the
Variance of that feature.
Right.
Yes.
Thank you.
So in the second step of this equation, we're taking phi x transpose out. But
Just take inside. It's a common in all terms, right? Just take inside.
I also didn't understand the second step.
see, W is equal to
This is the linear combination of the data points. W is the linear combination of the data points, right?
W is a linear combination of data points, and you already mentioned it as W is equal to phi x alpha. Now, when you're
This
taking
is okay. So this I'm taking alpha W star as phi of X alpha, or even you can write it as alpha is phi of X is summation
that is
over all
scalar
the data
multiplication.
points.
That is scalar multiplication. That is clear. When
Yeah.
you take the transpose,
Hmm?
so you are switching the transpose out of the bracket and bringing the other one into the bracket, or how is that? Because
Okay.
in the
Okay.
first part of the
That is the.
I think, are you doing this, sir? A transpose B is the same as B transpose A. Is that what
Okay.
you're doing?
Okay. This transpose should be here.
yeah, this is where I was actually.
Yeah, that makes sense a bit.
Yeah. Sorry about that. This transpose should be here. Yeah. Correct.
And then this becomes phi xi transpose into phi xi, which is basically kxi.
KX. Yes. Yes.
Okay. Okay, yeah, now it makes sense.
Can you take the example? Like where is
Yeah.
supposed
So the one that is given in the graded assignment, I'm taking that example. Yeah, it's not. Okay, so in this particular example, question number 7, in the graded assignment 5, you can check it out. I'm just mentioning what is there. You have been given that in this example, you have been applying a kernel regression with a polynomial kernel of degree 2 on a data set, and you are saying W vector is given by X of W vector is can be written is given by W vector is given by phi of X, and transpose some values like 0.3, 0.3, 1.6, 4.2. This is 1.6, 4.2 is minus 0.5 and 0.9. So this information is given to you that we are applying a polynomial kernel of degree 2. So your kernel is what? K xi xa is what? This is gonna be your xi transpose xa plus 1 raised to power 2. So this kernel you're applying on a data set, and your W beta is coming like this. So what is your alpha? Alpha is gonna be your 0.3, 0.6. This is your alpha actually, right? Now what you have to find? You have to find a prediction for the point 0.00000. This point you have to find the prediction. So what is the prediction? My prediction is given by alpha I, k, xi, xa, xt. So this is your xt.
Could you go a bit slow? I'm not able to.
So question says that you have been given a data set, and you apply the polynomial kernel of degree 2 on this data set, and the weight vectors has this form. Okay, this is what given in the question. Now you have to find a prediction for this data point xt. Okay. Okay, so you have been given polynomial kernel of degree 2. So the kernel function is xi xj transpose xj plus 1 raised to power 2, right? Now what is alpha? This is your alpha, right? So W is a linear combination of data points. So remember, this is your alpha.
Yes.
So how you find the prediction? Prediction is given by alpha I k xi xt, right? Sum over all those I equal to 1.
Yes.
Right. So here the missing information, you are not given the data points xi to xn. You are not given to those data points. But what you are given that the xt is 0.01, and this is your kernel function. But if you observe this thing, if you take the product of any data point with the 0, this xt is 0 vector, right? So if you take the
Sorry, I didn't get that. Sorry, xt is
this 0 vector, right? So if you take the dot product with any data point,
because it's a 0 vector, it will always turn to be 0.
It is always 0.
Yeah,
right?
yeah.
So the kernel function value with any data point, and for xt it is always gonna be 1, right?
Yeah.
Okay.
For any I, for all I, or say.
Yes.
What is alpha I? Alpha I are this thing. So 0.5. This will become 0.5 plus 0.6 plus 4.2 minus 0.
It will be simple sum.
Simple sum. That's
okay, got it.
And this is now the prediction of xt.
xt, yes.
But if we're given xt is 0,
xt is 0. What is the prediction for that?
Oh, okay. Sorry. Yeah. So the prediction is just the sum of these alphas.
Yeah.
Okay.
In this particular case.
Yeah. Thank you.
If xt is different, then what will be the approach, sir?
Then you definitely need xi in that case. Otherwise, you cannot find this kernel function value, right?
Okay, sir. Thank you.
Sir, if x1, I mean the xi xj. So in terms of data points, okay, is given like 1, 2, and other point is given as like 2, 3. So how going to put like xi, xj, which I mean, should I take the first x term or like y term? I mean, what should I take over here?
So let's say you have been given x1 as 1, 2, 3, 4, 5, and x2 is let's say 1, 3, 5, 7, 6. So in this case, just take the dot product of the 0, 0, or say the data point is 1, 0, 1, 1. This thing. Right now you have to find a prediction for this. Now you need definitely these data points. How many data points? And data points. Or let's say in this case you have been given only 2 data points. So not 2 data points. So you have how many alpha? So you have 1, 2, 3, 4, 5, 5. So 5 data points here, right? So x5, 5 data points you have been given. Right? So for every xi, x1, so you will find kernel of x1, xt, kernel of x2, xt, and just take the product with alphas, and then sum over all those things.
So we'll be taking the dot product in case of the polynomial function. If xt was not 0, 0, we would have taken its dot product with all the other data points
This function,
and added 1 and squared it.
square data.
That would be each k xt xi xt or xt xi, and then we would multiply by alpha I, the 0.00, right?
Yes, yes.
And sir,
And what is Gaussian kernel? What is Gaussian kernel?
Forgot.
So the radial basis kernel, right?
Yeah, what is the formula for that?
Sir, exponent to the power minus of y minus
Let's say xy, X kernel for xy.
acha, this is kernel for xy. Right, sir. So, sir, in that case, the Gaussian kernel resolves into
Remember this formula as well. E raised to power minus norm of x minus y square upon 2 sigma square.
Norm of, sorry, x minus y square.
Yes.
2 sigma square, okay.
This is Gaussian kernel.
Can you write it on a separate page, please? It's when we actually go through the notes later, it will be better if you
This
put
is
it on.
Gaussian kernel. So for kernel A operating upon x and y, this is your e raised to power minus norm of x minus y to whole square. And you can cross check if I've done some mistake here. So you can check in week 2. So I think this is correct.
yes, sir, this is the right formula.
and sir, if the kernel is polynomial degree 2, 3, or 3 or 4, then the power should be
Degree
3.
power should be degree.
Okay, okay.
So these are two standard mapping, the polynomial kernel and this standard Gaussian. These are the standard mapping. So this dimension is takes you. I mean, you started with some d dimension, and then the transform one. What will be the dimension for that?
We must write in this box Gaussian kernel so that when we read these notes, just remember. Just in
This
just
thing?
above this box, yeah, if you could, please.
Okay, so you want these rough slides?
Yes, definitely.
Yes, sir, don't erase it. Just upload it.
Yeah,
The
just
same.
in this box, if you could write Gaussian.
Gaussian kernel.
Yeah, please.
One doubt here. There, for the polynomial kernel, we have written as k of xi x test point. Here, x comma y. What that y is? That is also test point. Or it is a little confusing.
Any data d-dimensional data points. So kernel, where do you define kernel function? Kernel define you d into rd to rd to r, right?
Yeah.
That's how you define the so inputs for this function are d-dimensional data points. This is the one data point, second data points, and operate upon those things. And the output should be this real number. So this real number actually correspond to phi x transpose phi y. This is how you define a kernel function, right?
Okay.
Okay, I think we should move to the week 6 now. We are already late. Okay, so I think Okay. So I think slides are visible for week 6, right?
Yeah.
Okay.
Yes, sir.
Okay, so we have estimated W vector and the estimations comes like, so the estimated values comes like when we solve the estimation problem, W comes like XX transpose inverse XY, like using normal equations. So this is the estimation of W using the zero mean Gaussian normal. But if you look at this estimate problem, the MSE, the risk that we define, right? So remember the MSE for a estimator. So this is defined as expectation value of, let's say, W hat is the estimator minus the true value is W, then the square of this thing, estimation of this thing. Remember this MSE for define, we define for any estimator. So if you look at the MSE for this estimate, it comes out to be this thing, this sigma square trace of XS transpose inverse. And this quantity actually depends upon two things. One is the variance of this error thing that we assume, like remember we assume the error to be normal 0 sigma square. So this MSE for this estimate, so this estimate WML is actually comes out to be sigma square and trace of XS transpose inverse. And trace of XS transpose inverse is what? It's just you can write as so if I call lambda I, lambda D to be the eigenvalues of XX transpose, then what will be the trace of XX transpose inverse?
Sum of this.
1
Sum
by
of,
lambda.
sum of these things, right? These things. Okay. So this MSE depends upon variance that we cannot handle because it's the fix of the error term. And this covariance like matrix, right? So inverse of the covariance like matrix, XX transpose. So they, this MSE somehow depends upon the features, right? How the features are dependent to each other's, right? So we want this MSE to be lowered down, right? Because if the MSE is higher, it means that your estimate can be far away from your true W. That we don't want. So we have to make sure that the W star that we have estimated, the MSE for that is not very high one. So what we can do here, we cannot handle sigma square. It's a constant. What we can do, we can handle this lambda i's, right? So so I'm defining a new estimator. So once I define this new estimator, if you look at this thing and compare with the original estimator XX transpose XY inverse XY, you see that in this case your MSE gonna be this thing, right? So if I choose this lambda to be positive quantity, so this is lambda is coming from the R positive. So I choose lambda to be positive quantity. This is gonna be increased. So eigenvalue is gonna be increased, and this entire term gonna be decreased down. So MSE you have lowered down. So this estimator will have the lower MSE than the estimate that we have got using the normal equations, right? For any positive lambda. Okay, so this particular estimate makes sure
Lambda is
that
the
you are,
constant value, sir. Here
it's a constant value,
we have to define it.
positive number.
Okay.
Can we go to the previous slide once, please? Okay, the first slide. Okay, here we're saying mean square error, that is maximum likelihood minus the
I
actual.
think this thing also called risk, right? If I'm not wrong, this is also called risk.
Yeah, it's called risk.
Estimators.
It's called risk. It's bias plus variance.
Variance.
Bias square plus variance.
No,
Correct.
bias plus variance, I think so.
No, bias square plus
plus
variance.
Yeah.
Okay.
Ravi, are you done?
Yeah, go ahead.
Yeah, Karthik sir, sorry, sir. Hello.
Yeah,
Just a
so
small request. Just a small request, sir. I'm not able to understand the connection between, like till in week 5. If you can spend a couple of minutes, then it will be really a great help. In week 5, we talked about regression, right? And we identified a weight vector so that our error is minimum, right? And that
yes.
objective was achieved. So now, what is the trigger point? What is the trigger point to go for this regularization part? That is question number 1. And then the question number 2 is like we are predicting y with the help of y hat, right? So for that we are identifying one W vector, but we don't know any true W because the expected what you are saying that W minus WML, But we are not aware about true W, no, sir. So from where we are getting true W? So these are a couple of very basic doubts. It may be that I am not able to connect the dots. I am doing some silly mistakes, but this connection I am not able to establish.
That's where I'm also stuck, Ganga Prasad.
Okay, so if I go on, if I do this thing, I will end up doing something else, like estimation problem, estimation things.
No. I'm not asking about you to do the derivation, sir. I'm just saying there some intuitive explanation, like intuitive explanation in the sense, okay, we got our regression model, which is giving us a minimum error, right? So now, what is the need to go for regularization? That is point number one.
Okay,
And point
so
number
let
two-
me
and
do
point-
point number one first. So
Okay,
here we are
okay.
calling this as a estimator, right? Estimator for the parameter W, that we are coming from some distribution normal W transpose Xi sigma square, right? That's where your data yi xi coming yi is coming from, right? And we have estimated this W to be this one, right? Now this
Okay.
is your unbiased estimator,
Hmm.
right? But this variance of this thing can be higher. So that's where your knowledge of statistics too, like estimation problem, comes into the picture.
Sir, these derivations are clear. That's
So,
what I'm
estimator has to
But there is nothing called true W, no? Like in case of Y, we know that what is my true Y and what is my predicted Y.
if you have true W with you, then there's no point of estimating it, right?
Right. So okay,
But
that's fine.
we know that there is some W, and we are estimating that W.
So yeah. So from where this W we are getting, like in the line you have written MSE equal to expected value of W hat minus W whole square, right? So
No,
from
no,
where,
we are not getting W. We don't have W at all. Right?
Yeah.
What you're saying is absolutely right. So that WML we have from the
correct, WML we have.
so
Yes,
W
yes.
we don't have, right? We don't know what the true W is. But let's say we estimate WML enough number of times and look at the difference between this and the actual W, it's theoretically that converges to a certain number.
अरे यार लेकिन again from where the true
No,
W
sir.
is
I
coming?
think here the W what we're talking about is a random variable. It's not an actual. I mean,
Yeah, estimator is a random variable that you
it's a
agree on.
random variable thing. So you just
Yeah.
take out this data samples. I mean, you take out the samples, right?
Hari, estimator is a random variable, but we are subtracting na W hat minus W. So this W hat is random, but what is this W? From where we are getting the true W?
We are not subtracting W at all.
Subtract नहीं कर रहे. I mean,
नहीं कर रहे हैं. It is just a theoretical way of approaching a number, right?
It's
If
like
I
you
do
can say variance. You can say variance, okay?
That's fine.
So no. Just think, okay, you have data points, okay? Data set is there. You take out the samples, okay? From data points, okay, what you do, you just find the W1 you can say. When we
So
are
I
saying
got-
it's a random variable.
I got your doubts. So you are saying how to solve this equation and get to this thing. That's what you are asking me.
No, that derivation.
No, he's not asking that. He's not asking that. He's saying we don't know this W, so how are we actually subtracting?
Correct.
Right? That's all. Right? But I'm saying we are not subtracting at all. What we are trying to do is, okay, see if this helps GP, right? So let's say for the sake of argument, we know W. Okay?
Correct.
Just for the sake of argument. Okay?
Yes.
And
So
we have
that-
estimated WML.
Now it makes sense. Now we have
No, hang
estimated.
on.
Yeah.
I'm saying let's say we know that W, let's call it W star, okay? And now we've estimated WML. Let's say I take the difference, okay? There will be some difference.
So that is
okay?
error. That is error.
Hang on, that is error. That's error, okay? Now let's say I keep doing this many times.
Yes.
Okay? And if I take the average of these errors, right? Every time there is an error, right?
Yes.
If I take the expected value of this error, matlab average of those averages, average of those errors, then that will be equal to sigma square trace of this. That's what it means.
So somewhere we are doing an assumption that we have some idea about true W, and then okay, sir.
So it's theoretically, see, this is all derived to theory. It will converge.
Okay, thank you, Vasu.
Right?
Thank you, sir.
So that's basically the point. It's like standard error, na? So
correct.
you take a sample and you take the mean and you say, do it enough number of times, the mean of this converges with the population mean. Right? We don't know the population mean, but theoretically we know it converges.
And if I recollect correctly, then I think in lecture professor had said that we cannot do much with this sigma square because this has to do with error, right? So ultimately we are left with the stress part, correct?
Yes.
Correct. I
Yeah.
think, yeah, you're absolutely
Okay,
right.
so I request you to please go through your basic fundamental concepts of this estimation thing, like what is
Sir,
bias,
there
what
is
is
no
variance.
problem in that mathematical aspect. I think Basu got it. Okay, thank you, sir. Let us proceed. Yeah.
Yeah, please go through that things.
Yes, yes,
If
yes,
you
yes,
revise your concepts of that thing,
yes,
that will
yes.
help greatly help in this understanding this. I think you are confused with how you are separating and getting this sigma square trace of
No,
this
sir,
thing.
you are still not getting the question. That the derivation of
Ganga,
expected. Yeah,
Ganga,
got it.
in the,
Let us not waste.
no,
Yeah,
no,
yeah,
no,
yeah.
don't waste. See, in the
Yeah.
first lecture, na, forget about it. In the week 6, na, in the first lecture, in the very first minute, he told why he using this thing actually. Just forget about everything.
Okay,
Just go
then I
through
will
that.
watch that again. Yeah. Okay.
Vasu sir, you explained so nicely. I think in the next batch for ability, you
Sir,
will be
sir,
the
go ahead, sir.
instructor.
Please, sir. Go ahead, sir.
No, I was a TA for Stat 2, right? So I've done this a few times.
Okay, okay.
Okay.
Thanks, but I'll take that as a compliment.
Yeah.
Yeah, thank you, Basu. Yeah.
Should I move ahead now?
Yes, sir. Please, please, please. Yes.
Okay, so now we have designed a new estimator, and we are claiming that this new estimator has a lower MSE than the previous estimator, right? That you agree or not? That this estimator has a lower MSE than the previous one
Yes, sir, that is right.
for any positive lambda, right?
Yes, sir.
And
Yes.
that's what we wanted. We wanted the MSE to be lower down. And we are seeing that this estimator has doing this thing. Okay, now we are looking for this estimator using some different approach as well. Now we have done MLE to find the estimate. We now do the same thing, the estimation problem, but using the Bayesian approach. So what Bayesian
And
approach is
this MSc we are talking for W, right?
MSE for estimator, yeah.
Yes, W. Yes. Okay.
Okay, so now what we are focusing the same thing, the estimation problem. Remember the estimation problem. We have to estimate it this W, right? So by I given xi is coming from normal W transpose xi, and this some sigma square, right? Okay, so again the same estimation problem. We have to estimate it these W's. So we are now approaching to the Bayesian approach. And what Bayesian approach says that this W is now a random variable and random variable, and now we are assuming this prior for that, right? So the prior for W we are assuming to be normal with zero mean and some sigma square gamma square I. So this is the covariance of the weight vectors, right? So this is the prior assumption for the W vector. And what is the next step for Bayesian approach, Bayesian estimation? How you find the Bayesian estimation?
So we assume the standard deviation to be 1.
So using prior, sir.
You take the
And
PDF and then multiply with the overall
Yeah,
class.
now you collect the sample, you will find the likelihood and then take the posterior. You find the posterior for W, right?
Yeah.
So posterior is proportional to the likelihood times prior. So likelihood was the probability of the observations given the parameter, and the prior is the probability of the parameter. And here we are assuming W to be coming from the normal with mean 0 and some variance. Okay, so here this is the point. Here we are assuming the zero mean for the weight vectors. Okay, so this is the point you need to notice. Okay, if you do these calculations like apply these probabilities and all these things, you will get this posterior thing. And this posterior is actually nothing but and we'll find the estimate MAP. I mean the maximum of this thing, mode of this thing, and even remember this norm prior is normal and the distribution is again normal. So the posterior is again gonna be normal, right? This conjugate prior thing, right? If you remember correctly. So the estimation problem says that the maximum of this thing, the mode of this thing. So mode is gonna be this thing.
Right. That's
This
what
is some,
one question I have, very fundamental question.
this is
Maybe
Samita.
later you can answer. When do we use the mean, and when do we use the mode?
So
Like
both are the estimates.
why are we
Both-
using map here? Why are we not using, let's say, the posterior mean? I mean, I'm very confused. When do we use MLE and when do you use MAP?
So these are two different approaches for finding estimations. MLE is one frequentist approach, and this MAP is the Bayesian approaches, right? So, and you are saying why you're not looking for mean, but in this particular case, it's gonna be normal. So the mode or mean gonna be constant.
Correct. So, but we are calling it MAP for a reason, right? Otherwise, we could have called this mean only, na?
We use okay. We use map in case of when we have posterior kind of probability.
Maximum a prior probability, posterior.
When we
Yeah.
have, what did you say? When we have?
When they
Hello.
Yeah, please go on. Yeah, sorry, I could not get it. What did you say? When we
The
have?
thing is that we use the map estimator in case when we try to find out the posterior probability, that kind of estimation when we are doing, when we are using the Bayesian type of modeling. And MLE is a special kind of map estimation where the prior is of uniform distribution. That's where I read it somewhere when I had the same kind of doubt.
Do you
That
have
is,
that material somewhere which you can share?
I'll check in my history. If I find it, I'll ping it in the chat box.
Yeah,
That's
please.
what I read somewhere, and that's what I think that is the best. That is the best explanation for using map and MLE.
Vrinda, you can also go to the discourse and ping it in the discourse.
Yeah, I'll just ping it over here if I find it right
Sure.
now.
Okay.
Anything
Okay.
helps. Thank you.
Could you just pause on the previous slide, please?
This one.
Yes. So from the first equation, that is of likelihood. How do we arrive at this? We're trying to maximize the likelihood. Okay.
Maximum the posterior of this.
Right.
We are fine. This is your posterior, right? Posterior proportional to likelihood times prior.
Yeah.
So this is posterior distribution of that. I mean, the posterior is proportional to this thing, and so MAP says that the mode of this quantity, this distribution. So mod is, I think, the finding the maximum for W, right?
Okay.
So this maximizing this thing, I mean, the you can
And
take
since
log of,
it's a negative value, we're trying to minimize them.
yeah. So you can take the minimize of this thing, right?
I'll be very honest. I think I understand what GP is going through.
Hmm.
For me, there are two or three things that are just not making sense. I'm
Okay.
not able to relate why from linear regression we're coming to MLE. I mean, is this part of solving the linear regression, finding that W? Just another method of doing it, like we did gradient descent and everything?
Yeah.
So
So
gradient descent and all is the different methods to finding this optimization problem. Remember the
Of
optimization
a
problem was?
linear regression, right? There was the normal equation, there was the gradient descent, and then this is the third method.
no,
No,
this is
no,
the fourth method. There was an MLE.
no. So that probabilistic view is a different base to looking at the same. Our problem
Yeah, that
was
was not really a solution method, right?
that is not a method for solving the optimization problem. MLE
Yes.
was not that. Our, remember where we started with. We are saying that there's some function which is generating y, right? And our task is to find this function. The same problem we are looking at.
MLE is not a method to find W, that the as part of the linear regression.
No, MLE is ways to estimate those W's.
So it is a third method, isn't it?
Third
To
method, what
find
is
the
the
W
first and
of the
second
linear
method?
Yeah.
regression.
So see, see, if you take the linear regression and phrase the loss function or the objective function, you're getting a certain objective function, right? There, it's purely frequentist approach in the sense that you're just saying, I have this data, I have this, I'm kind of creating an objective function, right? So that's clear, right, to you?
The
The
objective
first,
function is basically to minimize error.
yeah, that's loss function or objective function,
Yes,
whatever it is.
whatever the loss would be, and it would be defined in different ways for each of these methods.
No. Don't come, don't cut across methods. First one you understood, right?
Yeah.
Right now,
Yeah.
there is no probabilistic view. We are not saying how the data is being generated, or we are not saying anything about it, right? So let's say we take a probabilistic view of the whole thing, right, and approach it differently. You still end up with the same objective
Error.
function,
Yeah.
same objective function, right? So they're
Right.
saying whichever way you look at it, you are coming to the same thing, right? It's just
Yes.
the whole
The objective function we arrive
algorithm.
at is the same.
Yeah, so whichever way you look at it, basically linear regression, if you look at it purely algebraically or you look at it probabilistically, you are still solving for the same problem.
Right.
That's what it says. That's all it says.
So that's why we've said, okay, because if we take a probabilistic view, we still arrive at the same objective function.
Yeah,
And since we can do that, now we're going to MLE and Bayesian modeling. Is that what?
Yeah, that was MLE. Now Bayesian approach is slightly different because you take you make a little more assumption, you make a few more assumptions, or you have some more information about W itself, right? There you have no information about W. Here you have some more information about W, right? You're saying W could have this kind of distribution and things like that. And that's why you have this prior also, right? Prior, you're assuming prior to be a normal distribution.
Then what is this gamma squared and all that?
It will come, na? Gamma square will come later once you look at it.
We just said that the W, the prior of W is distributed with, I think, mean 0, if I'm not wrong, if I recall correctly. Yeah. And gamma squared, I didn't get the gamma squared what?
Gamma square is basically the
gamma squared I or what? Gamma squared?
Gamma square is basically the variance of the W. If you treat W as a random variable, it will have some variance, right?
Yes.
It's assumed to be gamma square.
That's it.
That's it.
But I think there was another term written with the gamma squared.
That is just to convert it into a matrix. If it's a, if it's one value,
that was an identity matrix.
Yeah, that's all.
Okay.
That's all.
Okay, so it's making a bit of a difference, although I don't even understand the whole point behind the regularization, but I think this is at least trying to connect the whole flow of things. Okay.
Yeah. So from what I hope I'm right, but Bayesian is basically if you have more information about W itself, about things,
how it's distributed.
Yeah, or some information about it, how it's generated, how it's distribution, then you use that because you have a better estimate. The idea is you'll have a better estimate.
Okay.
That's all.
Okay, so idea of regularization is that we assuming that the estimator we have calculated like WXX transpose XY, that we say that the variance of this is high, or say MSE is high, right? And we want to drop this down. And why this variance is high, there's possible reason for that is that there's some collinearity or say correlation between the features, right? So if there is correlation between the features, then in that case the variance of this particular W will be high.
Yes.
And we want this correlation to be neglected down, or say we don't want any correlation between the features. Okay, that's why we assume that the prior for W to be zero mean. Zero means that what we are saying here is that we are assuming that the W vector close to zero, right? That's what the zero mean means for W prior. And this makes sure that you are assuming that the features have no correlation at all. That's why we are assuming prior to be zero mean. Okay.
Okay, so taking W as with the mean 0 ensures there is no correlation between the features, and hence variance is reduced.
Variance is reduced of the estimator, right? So the whole idea of regularization is that we want to reduce the correlation of the features.
Okay.
But is that a basic assumption that the features are not correlated, or this is a hope?
If the features are correlated, then the variance of the estimator will be high.
So,
or MSE will be high.
Yeah, to answer your question, that's a very good question actually, Ravi. To answer your question, ideally your features should not be correlated.
Yeah, features should not be correlated. If they are correlated, then your model will have high variance, right? And to reduce your variance, or in technical terminology, we call it a overfitting problem, right? So to reduce this overfitting problem, we go for the regularization thing.
Actually, Ravi, there are 7 to 8 assumptions which we have to ensure before jumping into regression.
Yeah, but sir, somewhere I think, yeah, if I read correctly in week 5 somewhere, so the good high variance actually is good actually in terms of reproducing that the actual data points. So now
No,
this,
here you are
PCA, I
mixing with
think.
that PCA
yeah,
concept.
that's what I'm getting
Yeah,
confused actually
this
somewhere.
you are mixing with PCA concept. Let us not get into that. Yeah,
That is only for PCA. Yeah.
Yeah.
yeah, yeah.
So
Okay, sir, let us proceed. I think we
No,
had a good discussion on it.
they are variance. You can think as like how much information they are
So,
having.
Hari, this is bound to happen. Don't worry.
Yeah, it's all mixed up, sir. No problem, no worries, sir. Go ahead, sir.
Okay, one question I have here.
Mm.
If the features are very highly correlated,
Mm.
why consider two features at all in the first place? We can go with one feature, isn't it?
but which one?
How does it matter?
And how to
It will
If
choose
I know
matter.
the
if I can find a relation between the two,
Mm.
even in a design of experiments, if the features are highly correlated, we
Okay,
eliminate
okay.
only the
So what you are doing, you're dropping some features and retaining some features, right?
I'm retaining features which are going to make an influence. If y is equal to mx plus c is what we take it as, okay, x and this is done.
Yeah.
But if
So
I'm going to
that
solve
is also some techniques of I mean
Ravi, we can do this.
overcoming the problem of overfitting.
Yeah, we can do this using the Pearson correlation matrix.
So Ravi, there is in real life, you handle this with a lot of other practical. There are a lot of practical ways of doing it. I mean, all based on algorithms only, but there is, depending on the industry, there are set ways of dealing with this. Okay,
Yeah.
so we can talk about it later. I can give you what I know
Sure.
about the CPG industry.
Yeah.
May not be. See, the reason why you want to identify so that's what regularization does, right? It kind of picks up the one which has the most impact and drops the one which has less impact and highly correlated. That's because when you're building a model and later on using it, you want to have the variables which matter the most,
Exactly.
right? So you want to also pick up things which are face valid and it makes sense. You can track those variables, right? You are more confident about those variables than other variables, right? So which is why choice of those variables are high. The simple answer to your question is when there are multicollinearity, either you deal with that issue through regularization, or ideally, if you have a lot of variables and there's multicollinearity, then you run a PCA and use that as the input to your regression.
Okay.
Yeah,
But
both is
input
correct. And whatever you mentioned, like dropping some of the features and retaining some of the features, that is also practice is done. Like it is called subset selection, something like this, right? So
Yeah.
so this lasso is actually this techniques where so what's happened in rigid regression and lasso is in rigid regression weight vectors goes to close to 0, right? And lasso W vectors actually some of the weight vectors becomes exactly 0. It means that we have dropped those features for which the corresponding weight vectors are 0, right? So the same thing, whatever you have said, that drop some features and retain some of the features. That's what lasso does. It just drops some features and retain some of the features. And in the rigid regression, this gives the minimum in or say the weight vector which has the very close to 0 value. It is giving very less and I mean what to say that.
Close to
I
0.
mean,
Close to
yeah,
0.
close
Yeah.
to 0. It's not giving much importance to that features, this particular feature.
Correct.
Right.
Correct.
So
And
to add, sorry, sir, to interrupt.
Hmm?
There's a course which we're doing again, business analytics, and exactly what the question that Ravi had. One more technique is explained where the correlation is the regression is verified between various features, and that's how they come to a conclusion that which of these features have higher impact in terms of predicting the response variable. So there's one more way of identifying which
Yeah.
features should
So
be kept and which ones to be dropped.
you look at the standardized beta coefficients. That will give you
Yes,
the relative importance because it's standardized.
correct.
So that is one way of it. But his question is a little more fundamental to that, which is even before getting there, should I just drop some features at all if they're multi-correlationality? That's absolutely the right way to do it. You either you use PCA to reduce, but then those PCA principal components have to make sense, right? Because you have to give it some label or it has to make sense by themselves. right? Interpretability will be an issue with PCA, right? Because you're not, you're using it to predict something, and there's all that has to make sense. It's not like image compression, right? So then it doesn't matter. Or you look at correlations and see which are more correlated and drop the ones which are you feel are less important from a domain knowledge perspective. Third is you use things like Ridge and Lasso. So they between 3-4 things people generally figure out, and usually like she was talking about business analytics, you look at the standardized coefficients, and each domain has a certain way of doing it, saying that typically we do it this way, and right. So it eventually works out, Ravi. I mean, all questions are absolutely valid, but eventually it works out.
Absolutely, I agree with everything. Not absolutely agree. I understand what you're all trying to explain to me. The reason why I went to the question direct is because in design of experiments, normally when as part of Six Sigma, Black Belt, and all these things, whatever you are doing, usually with DFSS, there is something called design of experiments.
Correct.
There, if the variables are correlated, we naturally drop them based on the effect that is. What we actually have a prior understanding of the variables. If we see a correlation between two variables, we automatically drop because it doesn't make much of a impact on the final output.
Yes, even here you do it. All I'm saying is, even here you do it. All I'm saying is, what you drop and what you don't is a lot of times depends on what is relevant for the domain. That's all I'm saying. Right? Suppose you're explaining it to the chief marketing officer, saying that I've taken this parameter, this parameter, this parameter. Then he'll say, why the hell did you take this? This doesn't make any sense. This doesn't make any sense to the industry. You should take
some similar
something
basis. Whatever you're saying, some similar basis.
Exactly. So what you said, we are both saying the same thing.
Yeah. When I said how does it matter is because one of them will make one is going to be sitting prominently, the other will be responding to this. In a chemical reaction, one without a catalyst, nothing will happen. You put a catalyst, then they will start dancing together.
Correct. So, you're absolutely right. Got it.
Okay, so
can you further, sir? It is 10:30 approx. Yeah.
Oh, 10:30 already. Sorry to have distracted the entire.
So the whole point of this talk is that if there is multicollinearity problem issue with the data set, there is different ways to handle this. One is like that Mr. Vasu mentioned, like using PCA, dimensionality reduction things, right? Where you just reduce the dimension. One is like just drop some features and retain some other feature, which is called subset selection techniques. And regularization, one of the another techniques to handle those issues of within the data set. Okay, so I just want you to figure out what is the difference between this dimensionality reduction and the subset selection techniques. Okay, and check how they differ to each other, right? So the one techniques in dimensionality reduction you study is PCA, and Lasso is one of the subset selection techniques where you drop off some features and just retain some of the features. Okay, but there's some difference, and I think if you think you can figure out what is the difference between these two. Okay, so where we were saying that this is the posterior, and we ended up with the estimate that we obtained using the Bayesian approach is this one, right? If you solve this problem, we get the estimate for these things. And if you look at this problem, this particular problem, and the estimate that we have designed, right? So this estimator, remember this estimator we have designed, right? So if you solve this problem, you will get the same estimator that we have designed now. So this is again the same problem. Take the derivative, set equal to 0. You will get WMAP as this thing. Or I must have written this thing. Remember this what we have defined as, right? Lambda I inverse xy. So this what we have designed, and this what we are getting using the Bayesian estimation, right? So and this particular W is called the risk weight factors, and this particular problem is called regression. Okay, and what is it doing? It's actually, so I don't want to use the technical term, but it's called overfitting problem. So in one sense, you can say that it's actually trying to reduce the variance of the model.
So lambda is equals to 1 by gamma square.
Yeah, lambda is 1 by gamma. Lambda I am taking here is 1 by gamma square. Okay, so here these are the parameter, hyperparameter they are called. So they are some cross validation techniques to calculate these hyperparameters, right? So the whole idea of the regularization is to reduce the variance of the models, or say reduce the MAC of the model. Okay,
By reducing the correlation.
So again, yeah. So again, these are not only these are the techniques. There are different techniques to reduce the variance of the models. One of those are regularization. Okay. So if you look at the this thing, this is a square loss, again loss function. This is your regularizer. Where this is your hyperparameter, and this the norm of W vector. And this different. This is called Ridge loss. Okay.
Sir,
Okay,
could you
so
please scroll up to the last slide for a second?
sorry.
Could you please scroll? Yeah. So, sir, in this regularizer, we can basically replace 1 by 2 gamma square by lambda by 2, right? Because lambda is basically 1 by gamma square.
Whatever, this is the concept won't affect. You just call it a lambda or lambda by 2 won't affect. It's,
Right, sir.
anyway,
So
you are
it's constant.
fitting some fixed value problem.
Right, sir. Got it.
So this should be summation over that. I will correct those over slides. Or even you can write it as norm of x transpose W minus pi all square plus lambda norm of, right? So this is your Ridge loss. Okay, so what Ridge does, Ridge actually sends your weight vectors close to zero. It's not exactly zero, but close to zero. And it ensures that your correlation between the features has reduced down, because now you are giving lesser importance to the features, right? To some of the features. So that's how you make sure that your features are not related to each other. Okay, so same thing I've written down here. MLE actually the same as least square regression without regularization, remember, and MAP the same as least square regression with the regularization, or say the Ridge regularization. Okay. And remember those assumptions, right? So prior should be normal, prior code W should be normal with mean 0 and some variance gamma square I. And in this MLE, we assume the noise to be normal, 0 sigma square. Okay, so these assumptions are should be not be dropped, otherwise the result will be different. Okay, so actually I should not done all these things here. So this you can check it out in the slides as well. This is how where your actually this MAP lies with respect to ML things, and we have already done this in the previous section as well. But now I just go through all these things. So this particular optimization problem even can write like this, right? So you can think as this optimization problem like this. This is the Lagrangian of this optimization function and the constant, right? So these are the equivalent optimization problem. And what is this constant? Constant says that this is a what is in the two-dimensional space. If you have W as let's say W1, W2. So what this constant looks like? This is a circle, right? So this is gonna be your circle in two-dimensional space. So where you are looking your W, you are looking your W inside this circle, right? And there's a WML somewhere in the same W space, right? And this W space is the one where is the loss is minimum, the square loss is minimum. And where you are looking your WMAP or the Ridge W, you are looking inside this circle, and you don't want to go far away for this W. So if you look at this problem as a and if you solve this minimization problem, where this minimizes this thing, right? So you are minimizing this thing. You are minimizing this particular loss thing, right? So yeah, this loss, right? So I've forgotten the square thing, but you just remember this thing. So we are doing this minimizing constraint to this thing, and if you say that the WML gives the minimum loss, so this W that you are looking for will give some loss, but more than this WML, because this WML by design gives the least loss, right? Square loss. So that loss for W, so X transpose W minus by will be this loss, right? Will be more than this thing. WX transpose WML, right? Minus by. So this is okay, right? So this I can say that this is equal to X transpose WML minus pi for some C, some constant C, because this quantity is greater than this thing. For some, if you add some C here, then this will become. If you solve this equation, you will get equation in W and WML, and this equation gonna be your ellipsoid in two-dimensional space if you take W to be two-dimensional, right? So you can think as W to be surrounded by this, your W to be surrounded ellipsoid, and where it touch, and we are looking W to be inside this circle, and we don't want to go far from this WML. So wherever this touches this circle, this is gonna be a WML. Okay. So this is what in terms of where the WMAP lies with respect to WML. Okay.
Sir, one question. Yeah, sorry. Go ahead, Ravi. I'll ask.
No, go on.
Yeah,
I
see,
think
this WML, okay. So how this sphere actually getting increase here? I mean, how is going to touch over here actually? How will
Okay, so for different C, there will be different for different C, right? So what we want some W, right? Some W we are looking for inside this circle, but again we don't want to go far from this
Correct.
point. Why? Because this WML is giving the least square loss,
correct?
right? And again we are looking for inside this circle only, right? So
Okay.
where we will choose, and we won't minimize these things, right? And we are saying that this loss will be always greater than this particular loss, because this WML always gives the least loss, this least square loss. So we want W where the loss is C more to this loss, right? For some C, and for different C you will get these different curves, and you will choose one where it hits this particular this circumstance.
Okay, so that's what we're talking about, the ridge regression, the constant what we're talking about there, right?
So that's where the risk W lies with respect to WM.
Thank you.
no, earlier when you wrote that W x minus y is going to be greater than W
ML
ML
minus
x.
Y.
Yeah.
So this
Why
is the
is
loss
that?
in this
Why
is the
is
loss incurred by WML, right?
correct?
And this is the loss that you are looking for W risk, right? And this WML, this square loss is the minimum for WML. Remember, this is the square loss x transpose W minus
Oh,
Y,
it's the minimum. Okay.
right? It's the minimum for WML.
Okay.
So for any W other than WML, is this loss gonna be higher?
Okay.
Sir, just a question. Shouldn't the objective function have a summation?
Yeah, of course, yeah. This summation should be there. Yeah, I've forgotten this, but you can add this.
Sir, can I ask something? See, if we go back to the ridge equation, that almost I'm just trying to the one above. I'm just trying to reconcile. This is almost like a Lagrangian.
Yeah, of course. This optimization problem with thinker, this optimal objective function with this constraint. So Lagrangian will be this objective function plus some constant times
Lambda plus
constraints.
except that I would have expected lambda minus theta or lambda square minus theta, right, to be the GW.
Yeah, again lambda. So here, if you minimize minus lambda theta, so that is the same thing. If you minimize these things, won't affect, right?
Okay.
So minimization problem won't be changed.
One doubt here, the lambda doesn't play any role.
Lambda plays roles, because if you set lambda to be higher, then you are penalizing W to be high, taking higher values, right? Because ultimately you want to minimize these things. So if you set lambda to be higher value, you want W to be close to 0. Otherwise, this loss will go higher.
Okay.
Right? And if you set lambda to be lesser values, then you are allowing W to be close to WML.
Okay.
So what happens if we differentiate and equate it to 0? I have not tried.
Which one?
The equation, the one above. Yeah, that one. The Lagrangian. Yeah.
This you will get is like XX transpose plus lambda I.
Yeah, I'm guessing we should get that only if we differentiate.
Yeah, this only you will get.
Yeah, actually, I didn't think of it like that. It's just purely like a, yeah, correct.
Okay. Okay, so next part is rather than applying the squared, penalizing the weight using squared second norm, you can even apply L1 norm. And L1 norm is what? when you apply the L1 norm to the regularization, this particular problem is called Lasso problem. In this case, what happens? So the same problem, right? So here in this case, rather than looking in the circles, you are looking into this square, right? So remember the same problem again. So here constraint will change to this thing. So there, this constraint is there in the two-dimensional space. This is, you are looking inside this square thing, right? So the optimal value will lie somewhere at the corners. Okay. So at the corners, some of the weights will become zero. So what Lasso does in Lassos, the weight vectors actually tends to exact zeros value. So if you set higher values of lambda, most of the weight vectors will become zero. In that case, what you are doing, you are actually dropping out some of the features. The features that corresponding to those features, those weight vectors actually are not playing any role in your model. So in one sense, you can say that you are removing those features in the Lasso.
Could you please tell about L1 norm and L2 norm?
So L1 norm is L1 norm is Lasso one, and L2 norm is this ridge loss, this regression. So L1 norm is defined as like for any vector W vector, let's say. So W is your W1 up to W2 dimension, right? So your L1 norm will be defined as, just take the absolute values of every element and sum over those.
Okay.
And for L2 norm, you define as take the square of every element and sum over all those things.
So it is the L2 norm that we have been doing most of it, using most
Yeah,
of
so
it.
this is L2 norm.
Euclidean distance, no? That is L2, right?
Euclidean distance, if you take the distance of W minus some other vector,
Yeah.
x minus y, take the, so this becomes the Euclidean distance of x and y. So it's like x1 minus y1 to whole square plus x2 minus y2 to whole square. The square root of all these things, right?
Yeah.
So in L1, instead of squaring and then finding square root, we just take absolute values.
Here in L1, we take the absolute values. Here we are taking square and then
Finding square root.
square root of this.
Thank you.
Okay, so remember the difference between the ridge and lasso. Ridge sends weight vectors near to zeros, and in the lasso, they become exactly zeros. Not all, some of the features, right? So it means you are sending, you are not, you are dropping out some of the features. Here you are doing very less importance to those features. So that's why this is called selections operator as well. Selection operator. What left? I think done with most of the thing, right? Yeah, Lasso doesn't have closed form solution because remember this, if you trying to solve this problem, the derivative doesn't lie because these are the absolute function, right? This absolute function, and the derivative doesn't lie at the corner points. Because zeros bed w equal to 0 point, the derivative will not define. So this particular problem has no closed form solution, and that's where we go for subgradient methods. So the subgradient, you can think like this is a function. Subgradient will be a vector. Let's say I am to find this, the derivative of this function is not defined at this point. So I will define a subgradient at this point. This will be a vector which is always down to this function, right? At any point. So that is called subgradient. And you may have different subgradient at the same point. You may this may be a subgradient. Again, this may be a subgradient, right? So
we can use subgradient in Lasso.
subgradient methods are used in Lasso.
Okay, not in Ridge.
Ridge regression. Ridge regression is has
No,
closed form solution.
Yeah, not
And
in
even for
regression.
the gradient methods, you can apply gradient methods in Ridge and Lasso as well. If the Lasso doesn't have gradients at every point, so we go for the subgradient methods.
Okay, for Lasso, you only go sub. Okay. And so at the end, if it is possible for you to give an example of numerical, which type of numerical uh, is related to this Ridge and Lasso regularization, then you can, or
Questions on
maybe,
what?
sir, numericals or questions on this Lasso and Ridge.
Numerical questions?
Yeah.
Sir, I think what he's trying to say, like yesterday we solved some, 8 to 9 question on regression, week 5. So we got a fair idea, right? So what kind of question we can expect related to week 6, like the numerical type. So what kind of numericals may come? Maybe that's what he's trying to ask. Even he's not trying to ask. This is my question also.
Yeah, same
Like
here,
what?
sir. Same here, GP.
Yeah,
Good to
like
you.
what kind of questions we may get from week 6, like numerical based or concept based. So if
No,
numerical,
mostly conceptual based question will be there on basics, not like finding the laws or finding weight vectors. Some such kind of questions won't be asked. Mostly conceptual based questions on these things. And one thing I missed in week 6 is that cross validation techniques, right? So
correct.
remember here lambda and in the regression you tell eta is to be learning rate. These are the hyperparameters, right? And for finding the hyperparameters, you have uh, different techniques for cross validation techniques. So one that we have discussed here is uh, like cross validation technique, which is called k-fold techniques, right? So in what we do in k-fold cross validation techniques, let's say you have 100 data points, 1,000 data points. So what you do, you divide into k-folds. Let's say 10 folds. You are doing 10 folds cross validation technique. You divide into k equal size 10 folds. So every fold will have 100 data points, right? What you train your model. You fix some lambda. Let's say lambda I'm fixing at 1. I train my model for 9 folds and evaluate my model, or say validate my model on the remaining fold, right? So I'm training my model onto 900 data points and evaluating on the 100 data points, or validating over 100 data points. I do over all such 10 possible combinations, right? One, I'm validating over this thing. I may validate over these things, and remaining I can train. I can validate over this fold and train over remaining 9 folds. So similarly, I will train 10 models for this particular lambda, right? And validate over 10 folds, right? So I will take the average error, or say validation error for all such 10 models. I'm saying that, let's say that loss to be alpha, cross validation loss. Again, I said I do the same procedure for some different values of lambda, and I'm calling that cross validation loss to be L2. And similarly, I will do for some values of lambda, and I will choose the lambda for which the validation loss is the minimum. So this is called cross validation techniques, where we divide our data set into k folds, train the models into k-1 folds, and validate the same model onto the remaining fold, and do the procedure again and again for different values of lambda, and then choose the one which gives the minimum loss, validation loss.
So what is lambda equal to 2? So when you say different values of lambda, so what do you mean by lambda equal to 2, sir? So
So
shall we take the 2 points over there? I mean, 2 blocks in that.
no, this is the value of lambda, right? We have to find the value of lambda, what value of lambda will suit our model. So you started with some random value lambda equal to 1, and then you will go for, let's say, 0.1. Let's say you go for 0.01. Some different values of lambda you have picked up, and you will choose best one.
So actually, in our the assignments also, we see the how many iterations we require for this solution, but I didn't see any numerical based on, okay, how to find the value of lambda and whatever you just shown. I didn't find anything here. I'm trying
Yes,
to find all an
again,
answer.
so if you do the numerical kind of question, then you have to train your model 10 times, right? For a single
Yeah.
lambda value. Again, you will train your model 10 times for this particular values. So that all computations you have to do.
So,
Okay.
sir, Nita is the learning rate. I know that. So,
Hmm.
what is the lambda we called?
It's a called regularization parameter.
Okay, 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 okay.
But sir, from week 5 there will be numericals, like whatever we have solved yesterday.
Not a very hard numericals, kind of like you have to find laws, or for any 3 by 3 matrix and all. Such kind of questions you cannot expect, but you should have ideas how to do that questions.
Yeah.
But
So yeah, in a nutshell, like week 5, from week 5 there will be numericals, and from week 6 there won't be any numerical. From week 6, concept based question will be there, right?
mostly concept based questions, but it's
Okay.
not like you can not do laws for one single data point and all that.
Okay.
So for by and large, from regression, we will be receiving numericals related to linear regression.
No, I'm not just saying that you must will
I
get.
mean,
You may get.
by and large, we may get from Lasso and Ridge, but we can expect that there would be a greater chance of receiving questions based on linear regression.
Linear and kernel also.
Linear and kernel.
Yes, yes.
Right, sir. And sir, from week 6, just regularization and other theoretical concepts.
Yeah. Okay, so in week 6, just remember these things. Why you need regularization, right? And how? What are the different ways of regularization? One is called ridge regression. One is lasso. What ridge does, what lasso does, and you can remember where your solutions with respect to WML lies of this ridge and lasso. Okay, so lasso actually the corner points, and in the lasso where it touches your circle, right? So that you can remember these things. So ridge and lasso, and why we need regularization, because we say that if there is some correlation between the features, then the variance of the model increases, or say the MSE of the model or say W increases, right? And we want to reduce that, and then we come up with some different estimate for W. So this is the whole idea of week 6.
And sir, one more thing, sir. So we will penalize the W,
Mhm.
okay, by doing L1 and L2. So, sir,
Mhm.
which regulation will more penalize the W or the error for the higher weights
So that depends upon the value of lambda
for both, for ridge and lasso?
for both ridge and lasso.
Okay, okay.
Okay.
Yes, sir. Yes, sir. I think that's all from
Yes,
week
sir.
6, or there is still left something.
So I think all are done from week
I
5
think
and
we are done with week 6.
Okay, sir. So can you upload these two slides as it is without
yeah, yes, sir,
erasing
of
the
course.
rough work?
Yes.
So when we are planning to have week 7 and 8, sir?
We haven't decided the date, but we'll let you know about the dates of for week 7 and
So
Yeah.
before Friday, I will take, sir. Before Saturday, sorry, before Saturday till Friday.
Anyhow, on Saturday we'll be having mock discussions. So before that, we should cover.
Can we take tomorrow if possible? Week 8, at least. Week 8 is very important, sir. I mean,
Yeah.
I can keep more
tomorrow. I'm
weightage.
not sure we are able to take this. We will let you know the timing for the other sessions.
Okay, sir. Okay.
So we just have 2 days now, sir. So when
Yeah, I
you
know
just
that. Yeah.
Yes, sir.
2 days.
I think what Hari is saying, sir, that correct. Like we can cover week 7 quickly, and then we can give more focus to week 8.
I
yes,
think week 7, week 8 are pretty easy weeks.
so week 8
Comparatively,
is
yeah.
we
Week
found week
7
7
is
easy.
okay. Week 8,
Yes, sir. Agree.
we need some time. Yeah.
If we take earlier week 8, sir, so will be very easy. I mean, good for us. So we can, we can come with some questions and query in the next session.
Yeah, that is right.
Yeah, we need time for week 8, sir. I mean,
Okay. I think week 8 was easy as well. Like
sir, for
only
you, sir,
applying
we're not
base.
talking about you, sir. We're talking about us, sir.
we, for week 7, we are also saying, sir, it's okay. Even we can give half an hour. That's okay. But for week 8, we need some time, sir.
But we will decide on the timing for week 7, week 8, and then we'll let you know about it.
Okay, sir.
Okay, sir.
I won't commit that it's gonna happen tomorrow or day after tomorrow. But
Okay.
before that, before exam will definitely happen. Yes.
Okay, sir.
Okay, sir. Okay, sir. Thank you, sir.
Thank you, sir.
Thank you, sir. Good night, sir.
So are we done
Thank
for
you,
today,
sir.
sir?
Thank you,
Yeah,
sir.
yeah.
Okay.
Thank you.
Thank you.
Good night.
Good night, sir. Thank you. Thank you. Bye.
Thank you, sir.